All right, let's get this started. All right, I'm going to share my screen and get this rolling. All right. So guys, this is the start of the 9 weeks. Not exactly the most fun and engaging way, but I'm going to work as hard as I can to do that for you. When you log into Classroom, you'll notice quite a few things listed. Don't worry about too much of this. For instance, this speed response, super simple. It's going to be in the PowerPoint. This one we will go over in just a minute. The movie assignment, y'all know what that is. And week 10 notes. So we're going to go ahead and jump into week 10 materials. I'm also going to be posting this video, which of course everybody's going to be able to see because nobody's viewing this right now. We're going to go ahead and get this rolling. There is some math involved today. So those of you that have a book, if you want to follow along, it is located on page 326. I hope everybody is having a decent enough day. Kind of a nasty start to this 9 weeks. So chapter 11, motion, located on page 326. Hope y'all don't mind my music going in the background. It's kind of the easiest way that I can fill the empty space that is in this classroom. All right. The standards, we're going to analyze data to support Newton's second law of motion, design, build, and find a device that works in a given constraint, hopefully. What is needed to describe motion completely? All right, so we're not going to be doing this, unfortunately. So we're going to go ahead and move straight on to vocabulary. Frame of reference. This is a system of objects not moving with respect to one another. So in our instance of football, my experience of one frame of reference we used quite a bit was the 40-yard dash. You have a set start point, you have a set end point. And that's how we can determine how fast you can move in a given amount of time, is by having that start and end point being our frame of reference. This is a good indicator of using a frame of reference to actually see how something is happening that may be invisible to the naked eye.
I have a feeling that we are very close to a perfect demonstration. We're going to see that ball drop.
With the forward and backward momentum matched as close as they're going to get it, the pressure's on Grant for a perfect release.
I don't know about you guys, but that looked pretty good to me. Let's check the high speed.
It really looked good to the naked eye, but the judge in this case is the high speed.
Oh my God, it's like a cartoon. It's just in the air, it stops and it just falls.
Look at that. Fantastic. I mean, look, it doesn't move at all. It's going straight down.
Woo! We did it! We did it! Yeah! Vector edition! Woo! Velocity!
After 3 days of suffering, that single shot brings the myth to an end.
I can't be happier. We actually got the speed of the car to match the speed of the soccer ball, and we got a perfect straight down drop.
Ladies and gentlemen, the laws of physics are still hard at work.
So from our viewpoint, it was kind of difficult for us to see how velocity is still working along with gravity and how those two vectors canceled each other out. And we're going to talk about vector addition and subtraction here in just a minute. It's going to bring us to distance and displacement, the difference between them. So for instance, when you travel on the roads, let's say, to get to school, you travel a total of, like, let's say that you live 4 miles down the road, and then you have to take another 2 mile off. You in total traveled about 6 miles, but your displacement is going to be different because displacement only refers to where you started and where you ended, whereas distance is the entire time traveled. And that's going to bring us to relative motion, which is in relation to a frame of reference. Now, just like in that previous video, relative motion relative to the car, it was moving away from it, the ball was. But in relation to the camera, however, it was stationary. It was just straight up dropping straight down due to gravity. And relative motion is something a lot of people struggle to wrap their mind around because, especially when we apply it to a global standpoint and a heliocentric model of the Earth, most people are like, well, it can't be spinning because I can't feel it and all that good stuff. What the difference is that you are used to feeling that motion in relation to the ground. You are not moving, but in relation to the entirety of the universe, you are. And it's going to bring us to this quick little video. It's 6 minutes long. Why am I doing this? Any of y'all need lotion?
How fast are you moving right now? That seems like an easy question. The first tempting answer is, I'm not moving. Upon further reflection, you realize that maybe the Earth's motion counts. So a second tempting answer is 19 miles per second around the sun. But then you recall learning that the sun moves around the center of the Milky Way galaxy. And the Milky Way moves within the local group of galaxies. And the local group moves within the Virgo cluster. And the Virgo cluster moves within... How fast are you moving is not an easy question. When mission control tells astronauts how fast they're going, there is always an assumed standard of rest. At the start of the voyage, speeds are given relative to the launch pad. But later, when the launch pad is just one more arbitrary place down there on Earth's spinning surface, speeds are given relative to the idealized, non-spinning, pinpoint center of Earth. On their way to the moon, Apollo astronauts had a hard time answering the question, how fast are you moving? Speed away from Earth was one thing, and speed toward the moon was quite another. That's because the Earth and the moon move relative to one another. Ah, of course, speed is a relative quantity. When Captain Kirk asks Lieutenant Sulu if the Starship Enterprise has reached a speed of warp 7, Sulu should reply, relative to what, Captain? Such a sassy reply may get subordinate Starfleet officers in trouble, but it is the only good answer to the question, how fast are you moving? This is basic relativity talking, not fancy Einsteinian relativity, but good old-fashioned and still correct Galilean relativity. Galileo seems to have been the first person to realize that there is no such thing as an absolute speed. Speeds are relative. This means that speeds only have meaning when they are referred to a reference frame. Presumably, that reference frame is itself at rest. But then we have to ask again, at rest relative to what? Because even the concept of rest has lost any hint of absolute meaning. Speed is relative and rest is relative. Earth's speed is 19 miles per second relative to the sun. The Enterprise's speed is warp 7 relative to the center of the Milky Way galaxy. Your speed is 0 relative to your easy chair. But depending on where you sit, it is hundreds of miles per hour relative to Earth's center. When we furrow a brow and ask, but how fast is Earth really moving? We imagine spaceship Earth plowing through the ocean of space as it orbits the sun. But space is not an ocean. It has no substance as water does. Space is not a thing. Space is nothing. Space is no thing. You can move between 2 points in space, say between Earth and Mars, but you can't move through space. There's nothing to move through. It's like trying to say how much a hole weighs. A hole weighs exactly nothing, because a hole is nothing. It's a void, and so is space. To move relative to nothing is meaningless. The concepts of speed and of rest have only relative meaning. They are absolutely meaningless. They mean something only with respect to arbitrarily chosen, artificial frames of reference. If someday you are buckled into your spaceship and you see from the side window, say, a space station whiz by at constant speed, there is no way to know which of you is really moving. Neither of you is really moving because there is no deep reality about constant speed. Constant speed in a straight line has only relative meaning, a kind of relative reality. Does this mean that all motion is relative? No. Some motions have only relative meaning, but some motions have absolute meaning, are absolutely real. For example, constant speed is relative. But constant velocity is absolute. 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 Constant velocity is absolute but change in speed is absolute. Calling something absolute in science means that arbitrary standards are not used in its measurement. It is unambiguously measurable. When your spaceship fires its engines, your change in speed is beyond doubt. You feel it in your stomach, and your ship's sensors can measure it. Outside your window, the passing space station may seem to be changing speed, but the beings inside the station will not feel it, and no sensors can measure it. You are really changing speed, and they really are not. There's something absolutely real about changes in speed. The same goes for rotation. If your spaceship is spinning, you can feel it, and your ship's sensors can measure it. The space station outside may seem to be going around you, but it is you who feels queasy, not the folks in the space station. You are really spinning, and they really are not. There's something absolutely real about rotation. So some motions are relative, and some are not. There is no deep reality about constant speed, but changes in speed are deeply real, and so are rotations. We have to be thoughtful in our analysis of everyday experience in order to identify what is deeply real. Since we can be fooled by perceptions as basic as speed, maybe every perception deserves careful scrutiny. This is what inspired Einstein to his incredible insights about the speed of light and forward time travel. Knowing how to identify what is deeply real is tough and important work. If a police officer ever pulls you over for speeding and asks, "Do you know how fast you were going?" an insightful, though perhaps unwise, reply would be, "Relative to what?" And then, as you sit in the back seat of the police car and feel it accelerate toward jail, you can add, "But some things are absolute."
All right, let's present, make sure that there's nobody in the waiting room. There is not. Okay. Let's move to the next one. All right, distance and displacement, the difference between them. Why is this not wanting to work now? All right, so the distance that you're seeing the ball travel, we're seeing that it's moving up and out. Now, the distance that it travels is going to be different the entire time. So let's observe it. And as it increases, we are only measuring the amount of distance between 2 points. But if we pause it at any point, we can actually measure how far it has moved away. Now, this is located on page 392 if anybody wants to double check on it. On page 330, we're not going to do that because we don't have a group. So the difference is that displacement is the direction from the starting point in a complete straight line. So from start to the end point, we're not counting the total amount of distance traveled by this ball, which can include the upper throw as well. So that is the main difference between displacement and distance. In this instance, what you're seeing is that all of them have the exact same displacement. All of them start at point A, which is down here at the bottom left, and end at point B. So all of the displacement, which is shown by this green line, is going to be the same. However, each of them have a distance traveled that's different among each one. So for instance, the red would have moved 1, 2, 3, 4, 5, 6 units up, 7, 8, 9, 10, 11, 12 units total. So we've moved a total distance of 12 units, whereas yellow would have moved 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Well, I mean, it's all basically adding up in this instance. But if we were to add curves and stuff along that nature, or if we were to, like, let's say yellow had to turn around, then we would have a difference in distance traveled. It just so happens that this is a, I'm trying to think. Anyway, my brain is fried right now. We're going to talk a little bit about vectors. How long is this video?
Dove Advanced Care's new
Anybody want
formula,
Dove
enriched
lotion?
with 1/4 moisturizers with natural oil, leaves underarms feeling healthy and protected, and you more confident and carefree. Effective protection, hand to skin.
Yeah, I'm gonna let this run.
Physicists, air traffic controllers, and video game creators all have at least one thing in common: vectors. What exactly are they, and why do they matter? To answer, we first need to understand scalars. A scalar is a quantity with magnitude. It tells us how much of something there is. The distance between you and a bench, and the volume and temperature of the beverage in your cup are all described by scalars. Vector quantities also have a magnitude, plus an extra piece of information: direction. To navigate to your bench, you need to know how far away it is and in what direction, not just the distance, but the displacement. What makes vectors special and useful in all sorts of fields is that they don't change based on perspective, but remain invariant to the coordinate system. What does that mean? Let's say you and a friend are moving your tent. You stand on opposite sides, so you're facing in opposite directions. Your friend moves 2 steps to the right and 3 steps forward, while you move 2 steps to the left and 3 steps back. But even though it seems like you're moving differently, you both end up moving the same distance in the same direction, following the same vector. No matter which way you face or what coordinate system you place over the campground, the vector doesn't change. Let's use the familiar Cartesian coordinate system with its x and y axes. We call these 2 directions our coordinate basis because they're used to describe everything we graph. Let's say the tent starts at the origin and ends up over here at point B. The straight arrow connecting the 2 points is the vector from the origin to B. When your friend thinks about where he has to move, it can be written mathematically as 2x plus 3y, or like this, which is called an array. Since you're facing the other way, your coordinate basis points in opposite directions, which we can call x prime and y prime. And your movement can be written like this, or with this array. If we look at the 2 arrays, they're clearly not the same. But an array alone doesn't completely describe a vector. Each needs a basis to give it context, and when we properly assign them, we see that they are in fact describing the same vector. You can think of elements in the array as individual letters. Just as a sequence of letters only becomes a word in the context of a particular language, an array acquires meaning as a vector when assigned a coordinate basis. And just as different words in 2 languages can convey the same idea, different representations from 2 bases can describe the same vector. The vector is the essence of what's being communicated, regardless of the language used to describe it. It turns out that scalars also share this coordinate invariance property. In fact, all quantities with this property are members of a group called tensors. Various types of tensors contain different amounts of information. Does that mean there's something that can convey more information than vectors? Absolutely. Say you're designing a video game and you want to realistically model how water behaves. Even if you have forces acting in the same direction with the same magnitude, depending on how they're oriented, you might see waves or whirls. When force, a vector, is combined with another vector that provides orientation, we have the physical quantity called stress, which is an example of a second-order tensor. These tensors are also used outside of video games for all sorts of purposes, including scientific simulations, car designs, and brain imaging. Scalars, vectors, and the tensor family present us with a relatively simple way of making sense of complex ideas and interactions. And as such, they're a prime example of the elegance, beauty, and fundamental usefulness of mathematics.
Not that I really need it. All right. So let's make sure that. All right, it's still picking up. All right, so the definition for vector is just a quantity of a magnitude and direction. That's on page 330. Resultant vectors are where we add in two or more vectors all into one. And it's just going to show the total displacement essentially. All right. I'll revisit that because I need to get through speed and velocity. How are instantaneous speed and average speed different? How can you find the speed from a distance time graph, and how do velocities add? So, first vocab word is obviously going to be speed. Speed is a ratio of distance and the amount of time it takes for somebody to cover or something to cover that distance. So, for instance, when I was going to college to play ball, I was running about a 4.6, which means that in 4.6 seconds, I could cover 40 yards. Examples of this are miles per second, kilometers per hour, and average speed, which is what most of you are familiar with, is the total distance traveled divided by the time it takes to travel that distance. For instance, your average speed at any given moment could be 60 miles per hour. That's what your speedometer on the car details to tell you. And the formula is located at the bottom. You can copy and paste that into your notes. Average speed equals total distance over total time. So, again, formula right there. So on page 333, you're going to read the math skills. I would prefer if you could read with somebody if you have that option. It should take 2 minutes, but it's located right here. Pause the video, read over it, make sure that you understand the basic concepts as well as the formulas. Speed and velocity. All right, practice problem. A person jogs 4.0 kilometers in 32 minutes, then 2.0 kilometers in 22 minutes, and finally 1.0 kilometers in 16 minutes. What is the jogger's average speed in kilometers per hour? All right, so first thing is that we need the total distance traveled. So we end up with 4 plus 2 plus 1, which should equal 7 kilometers. So our jogger, there it is, the jogger is covering 7 kilometers currently. Now we need to know the total amount of time that they spent jogging. So we end up with 32 minutes plus 22 minutes plus 16 minutes, which should equal, if I am remembering correctly, that should equal 16 minutes. Now, that means that our jogger is running 6 kilometers per every 60 minutes. Now, here's the problem. It's asking us in kilometers per hour. So, all we have to do in order for us to change from minutes to hours is we throw in the conversion factors. Now, that's a couple of chapters back, but boy, this sucks. This really sucks. Wow. Okay, anyway. So we're converting from minutes, so we're going to put that on top. Oh my gosh. And we're converting to hour. I'm going to pull this up now. Okay. Oh my God. Anyway, so we're converting from minutes, and we're going to be converting to hour. Okay, how many minutes are in an hour? I heard somebody at the back. He's a transfer student from Wisconsin. His name is Jimothy. So there's 60 minutes in 1 hour. So we end up with 7 divided by 60 multiplied by 60, which should give you 7 kilometers per hour. This really is not my forte. Trying my best though, I really am. All right, so per minute, yeah. I don't know why it was in a term of minute, but anyway. All right, train travel, did I do that right? Yeah, okay. All right, a train travels 190 kilometers in 3 hours, and then travels 120 kilometers in 2 hours. Calculate its average speed. Okay, let's move this down. I'm sure it's still recording. Oh, this is terrible. I'm sorry, guys. All right, a train travels 190 kilometers. Then it travels 120 kilometers. We end up with 9 plus 2 is 11. So let's see, that is 310 kilometers total. Then we need to calculate our time. So 3 plus 2 equals 5 hours. So that means we traveled 310 kilometers in 5 hours. If we want to calculate its speed, all we do is we take 310 divided by 5. So 310 divided by 5 equals, I have no idea because my brain's not working today. So we're gonna see. Yeah, there we go. Should be 62 kilometers per hour. There's some more practice problems. I'm not doing that for the note check. If you want to work on them. All right, you can turn to page 334, read the paragraph concerning instantaneous speed. As you finish, have somebody in your group, well, it's just going to be you today, add one characteristic to either average speed, instantaneous speed, or in the middle of the Venn diagram. All right, there's the reading located right there. And the Venn diagram is going to be on Classroom. All right, so that's going to bring us to the end of this. If I want to, yeah, we're about to be finished up. So using this, we're talking about distance covered at any given time. So we can see that as time continues, distance covered from the start point for each of these changes. So I want you to try and think which car stopped at a red light on their travel. That could be either red, blue, or yellow. Which car has their cruise control set? So which one is staying the same average speed throughout their entire travel, and which car has just left a red light? So just at the very beginning, left a red light. So the answers for that is which car is stopped. As you can see, the distance traveled is right here, and then our speed has hit 0. We are not increasing at all. We are not traveling at all. So our blue car is the one that stopped at a red light. The cruise control, as you can see, our distance is increasing at the same rate throughout the entire thing. That would be our cruise control, so red. And the car that just left a red light, as you can see, we are accelerating getting faster. We'll talk about acceleration in a minute. From 0. So that car, our yellow one, would have just left a red light. And combined velocity is an interesting thing.
Now we're going to
If
do
you've
another.
ever stopped at a red light or started rolling backwards, you will get the sensation that a car next to you is moving forward. And this is a visual demonstration of
To
it.
show how to compare the velocity of an object in one frame of reference to its velocity in another frame of reference. If I give this dry ice puck a certain start, it moves straight across the table with a speed which is essentially constant because the forces of friction have been made very small. This is just the law of inertia. An object moves with a constant velocity unless an unbalanced force acts on it. Now, will you give it the same start backwards? I'll try that. If Dr. Hume gives it the same start, it moves back in this direction with the same velocity. Now, we are on a car here, a car which can move and which really is going to move in this direction. And we're going to repeat the experiment. All right, let's go. If we were making measurements here, then we would observe the same velocities, that is the same experimental results that we did before. And so would you, because you are observing this experiment through a camera which is fastened to this cart. That is, you are in the moving frame of reference with us. But now we're going to do the experiment again, and this time you watch through a camera which is fixed in the Earth frame of reference. Now concentrate on watching the puck. Don't let your eye follow us. And I think you'll see that it'll move faster that way and not so fast this way, relative to you and relative to the wall behind.
So it's a pretty good demonstration of combining velocities. So velocity is a type of vector. It describes the speed and the direction that an object is traveling. As we can see here, changes in vector can be sudden. This is a, I forget where this competition is located at, but you'll see here that change in direction isn't a constant. We're constantly changing direction. And I want to see the slow motion. So here you can see the direction is changing, but we're still maintaining our relative speed. So velocity is changing. Read page 337 on combining velocities. Write the key phrases in your notes. Oof, that's pretty blurry. Try your best. Key phrase has a key in front of it. And we will talk about acceleration tomorrow. So, going to finish up with the distance, displacement, velocity, and speed. I'm going to click on it and it'll open up. And you will see that there are 2 sheets. Okay. Make sure that you're reading and following the directions, because for part 1, you're going to choose 5 problems. You have 6 total here. You can do extra bonus points if you wish. They'll be worth half the amount of total. So I think each of these are worth 5, so they'll be worth 2.5. But you've just got to choose 5 that you wish to work. And then on the second one, calculating speed, time, and distance. Going to use those formulas from the previous section that we just covered, and choose 5 to work there. Again, still bonus points, but if I have any questions, I'd like to hear from all of my students. Anyway, if not, I'll catch y'all tomorrow.